like what we call our double angle identities or formulas. So the first one is if I'm taking the sine of 2 times some angle u, this is equal to 2 times sine of that angle u times cosine of that angle u. We actually have 3 cosine double angle identities. For the most part, it is up to you which one you choose to use. Different ones are helpful in different situations. So the first double angle for cosine is cosine squared u minus sine squared u. The second one is 1 minus 2 sine squared u. And the third one is 2 cosine squared u minus 1. So all 3 of these are equal to cosine of 2 times some angle u. Typically, when we're using these, I prefer to use the ones that only have one trig function in them because it makes it a little bit easier to solve. But you're more than welcome to use any 3 as long as it fits with what you're trying to achieve in the problem. And then, as always, we have a nice pretty tangent double angle identity as well. And this is equal to 2 times tangent of the angle u over 1 minus tangent squared of u. So we're going to go ahead and do a couple of examples, and then we will get into another set of special angle identities.
How does it equal the same thing if it's taking the 2 sine squared u like minus and then also positive number? Shouldn't those be like opposite?
It works. I promise it works.
How
It works. Just trust it. Okay, so I'm going to minimize this a little bit so we can try and keep them on the screen, and then we're going to go ahead and do the examples over on that side. I'm hopeful that that makes it a little bit easier. So the first example we're going to do is, in my opinion, similar to 20 and 22 from the homework. Okay, because I know those are probably the big problems that you had. So this one says if sine of theta is equal to 4 over 5, and angle theta is an acute angle, find sine of 2 times theta and cosine of 2 times theta. So this one actually has 2 parts because we're finding 2 double angle identities. Give you guys a second to write that. Anytime I see a trig function of some unknown angle equal to a fraction that doesn't exist on my unit circle, what can I pretty much guarantee I'm going to have to draw? A right triangle, because I know all of my trig ratios come from a right triangle. Okay, so that should be the first thing you need to do. You also need to do that on 20 and 22 from the homework. So I'm going to draw a right triangle. I'm going to pick one of the acute angles to be my angle theta. It does not matter which one you choose. I always like to choose the bottom left one. I don't know, it's just habit for me. And then I need to look at the information that I have been given. So I have been given the sine of that angle theta is equal to 4 over 5. How does that help me assign side lengths for this triangle? Sine is equal to opposite over hypotenuse. So the side opposite theta is my 4. And my hypotenuse is 5. Through the Pythagorean theorem, then, we're going to get that our adjacent side is equal to 3. I trust that you guys can do that on your own and that we don't have to do that together in class. So now I have all 3 sides of my triangle, which is awesome because I'm going to have to be using some trig function when I do this identity. I'm going to start with the first one it asks me to find, which is sine of 2 theta. So I'm going to find the trig identity that has a 2 times some angle, which is going to be the top one.
So is it always going to be 2?
For a double angle identity, it's always going to be 2. Yes. So this tells me that sine of 2 theta is equal to 2 times sine of theta times cosine of theta. All I did was substituted theta in for u because theta was the unknown angle value I was given. But now I've run into an issue. I'm used to being able to pull these values from my unit circle, but I don't have a unit circle value associated with the triangle. So where am I going to come up with sine of theta and cosine of theta?
Triangle.
The triangle. All my trig values can also be found from a triangle, right? That's not new to us. Right? So we start filling it in. This is equal to 2 times. The cool thing is they already gave me sine of theta, so I don't even have to work for that one. Cosine of theta, however, I will have to find from my triangle. What is cosine on this triangle of theta? 3/5. Cosine is adjacent over hypotenuse. My adjacent side is 3. My hypotenuse is 5. And then I simplify by multiplying my fractions together and doubling my answer. So I multiply the fractions first. This becomes 2 times. 3 times 4 is 12. Over 5 times 5, which is 25. That 2 then multiplies into the numerator only, because that's the same as 2/1. And then my answer becomes 24/25. So sine of 2 times theta is equal to 24/25. Questions, concerns, or issues? Does that make sense how we did that? Okay, so that's part of what you have to do for 20 and 22 on the homework that was technically due yesterday, but some of you I think are still working on. You have to use a right triangle for some of those angle values. So now what we're going to do is cosine of 2 theta, because that was the other part that it asked me to find. I'm going to find cosine of 2 theta. The really cool thing here is I could pick which value I wanted to use, or which of the equations. I would like to use, just for practice, the top one. So the cosine squared u minus sine squared u. That's the one I'd like to use here.
Didn't you just say how you like using ones with only one?
I do, but it's good practice then to use the really ugly one in class. So cosine 2 theta using that top one is equal to cosine squared theta minus sine squared theta. For the purposes of solving this, I don't really like the way that one is written, so I always like to rewrite it anytime it has a square in it. This is equivalent then to cosine of theta all squared minus sine of theta all squared. That makes it a little bit easier to do the replacement and then the squaring to get my final answer. And just like before, I'm going to pull cosine of theta and sine of theta from the right triangle that I created. So I know that cosine of theta is equal to adjacent over hypotenuse, which is 3/5. So this becomes 3/5 squared minus, same thing for sine of theta, which is opposite over hypotenuse, which is 4/5. And I'm going to square it just like before. And then I'm going to put my answers together. So this is equal to 9/25 minus 16/25, which gives me a negative 7/25 as my final answer. Questions, concerns, or issues with that? Are we okay with that? Anybody have a major issue with anything that we have just done? Okay, let's do one more example. We'll move into our half angle identities. Huh? Sorry, Hetty. There we go. I'll leave it for a second.
Sure, I don't care.
No, I didn't know. I'm sorry.
That was like the least ideal spot to charge that.
It's fine. I haven't kicked it yet. It's okay.
I can look at it before I leave, so then every time I leave, I go, oh my god, I can put it back in my bag. That's good. Because if I'm still there, then I won't see it when I leave, and I'll just leave.
You go to Avos and then have to look.
I'm so glad everyone can relive this conversation when they watch this video.
Yeah.
It's gonna be so important.
And if
Are you done,
watch this
Jojo?
video-
Okay. Well, you know what? It's here in case anybody needs it. The next example that I would like to look at is a little bit different. So this one asks us to express cosine of 3 theta in terms of simply cosine of theta. What's the first thing that we notice on this problem? There's a 3. I don't have any identities or formulas that have a 3 times some angle theta, so I'm going to have to break that up somehow. What do I know 3 is equal to? Think addition. 2 plus 1. So cosine of 3 theta is equivalent to cosine of 2 theta plus 1 theta, right? So I was able to break that 3 theta up. And I have a formula for a double angle, and I have a formula for the addition of 2 angles inside a cosine function. So I am now able to simplify this based off of what we've done so far. So that's exactly what I'm going to do. I'm obviously going to start with the addition part of it, and then we'll break the double angle as we get farther in. So I need to go back to the notes that you wrote on Monday. I need to go to the cosine addition one, and I need to rewrite this using that formula. So what is cosine of angle plus angle equal to?
Cosine U times cosine B minus sine U times sine
So that breaks down into cosine 2 theta times cosine of theta minus sine of 2 theta times sine of theta. I'll give you a second to write that. And the way that we found that is we just went back to that first set of notes that we wrote. We found the cosine, that was addition, and then rewrote it plugging in 2 theta and theta in place of u and v. Everyone okay with how we figured out how to rewrite that? Yes, we're kind of okay? Okay. So now is where I want to actually go in and do some substitutions, because I can't do anything with this the way it is right now, but I do have some double angle identities that are going to hopefully help me break this down a little bit farther into just cosine functions, because that's what I'm trying to get this in terms of. So if I'm looking at cosine of 2 theta, I have 3 options, right? I have cosine squared minus sine squared. I have 1 minus 2 sine squared. And I have 2 cosine squared minus 1. Knowing that my end goal is to get this entire equation in terms of cosine, which one of those 3 options do you think I'm going to use? The 2 cosine squared theta minus 1, because the other 2 both have a sine in them, and that's going to make my job so much harder. So I'm going to replace I'm going to replace cosine of 2 theta with that 2 cosine squared theta minus 1 that it is equal to. And I pulled this straight from the double angle identities up above. Why did I stop at the sine 2 theta? Why didn't I write that down yet? Am I leaving it as sine 2 theta? No, I'm replacing it with what is equal to based off our double angle identities that we wrote down already. So what is sine of 2 theta equal to? And then I still have that sine theta at the end that I need to account for. So this is what I have right now after making the double angle substitution. Are we all okay with that step? So what we're going to do now is we're actually just going to simplify this a little bit to make it a little bit easier to work with. So the first thing I'm going to do is distribute this cosine into both of these terms inside the parentheses. When I do that, I get 2 cosine cubed theta minus cosine of theta. I'm gonna put my signs together on the right-hand side, and when I do, I get minus 2 sine squared theta cosine theta. So I just combined like terms where I could. Again, my goal is to get this all the way down into just cosine trig functions in here. Am I really, really, really close? Yes or no? Yes. 3 out of my 4 trig functions in here are already
Where did the
cosine.
one sine go?
I multiply them together. So sine times sine becomes sine
okay.
squared.
Why did you multiply it by the cosine?
Well, the cosine can't combine with the sine. They're not the same. So multiplied by it, it's still there. It just couldn't combine with anything. So we have 4 trig functions on the board, 3 of which are cosine, 1 of which is not. So that one that's not is the one that I somehow have to try and substitute because I need to get that in terms of cosine. Do I have anything at all that I know about that relates a sine squared into something with cosine in it?
The 1 minus 2 sine squared.
Well, that's double angled. I don't have a double angle here. I have a sine squared. So I have a Pythagorean identity that says sine squared theta plus cosine squared theta equals 1. And I can manipulate that around to get the sine squared theta by itself. Right? We all know we have an identity that says that. So if I want to replace the sine squared, I have to get the sine squared by itself. I'm going to subtract the cosine squared over.
Where's the cosine squared coming from?
At the Pythagorean identity that we wrote
Don't you?
weeks ago.
Yeah, but okay.
So I move some stuff around. Now that I have the sine squared theta by itself, what it's equal to, I can replace the sine squared theta with. So now my equation is becoming 2 cosine cubed theta minus cosine of theta minus 2 times 1 minus cosine squared theta times cosine of theta. All I did was replace the sine squared theta with 1 minus cosine squared theta that came from the Pythagorean identity. And then my last few steps are to distribute and combine my terms to simplify it. So I'm going to distribute this cosine in and the 2 in and see what I have. Everything over here stays the same. Multiply the cosine in, multiply the 2 in, I get minus 2 cosine of theta plus 2 cosine cubed theta. Take a second to work through that in your head. If you need to write out extra steps, you're absolutely welcome to, but this is what it will come out to be.
Wait,
Yes,
where did the cosine come from in this third one?
cosine times 1 is cosine. So I distributed this cosine into both terms inside of the parentheses, and I also distributed the 2 into both terms inside the parentheses. So cosine times 1 becomes cosine, negative 2 times cosine becomes negative 2 cosine. Cosine times cosine squared becomes cosine cubed. Negative 2 times a negative cosine cubed becomes positive 2 cosine cubed. So if you need the extra steps written out where you do each of those distributions, please write them out. And then from here, I would just simplify by combining like terms. Is there anything I can put together?
2 cosine cubed.
I have 2 terms that are cosine cubed, so when I put them together, I just add the coefficients on the front, which makes it 4 cosine cubed. Is there anything else I can put together?
Put the cosine.
The singular cosines, negative 1 and negative 2, makes a negative 3 cosine. And then I would be finished.
That's the answer.
That's the answer. How much did we hate that?
I don't
Alright,
see
let's
any point
fail.
in any.
Your homework is not that hard. I promise.
You say that all the time.
Or she's like saying, oh, this board translation is easy.
It's
I always get like a 3 out of 6.
What'd you say?
Are we all done writing this one?
Did you just say you feel like me right now?
No. She said, no, bad, right? Like how much like that. I was like, I was going from nothing to Colin, pretty close to Colin.
I thought it said past.
I like that.
Thank you,
Okay, so we are going to give the double angle identities a break, and we're going to look at our half angle identities now.
How many different angles are we learning?
There are 3 in this lesson, so this is number 2.
Colin, think about it. If you don't finish today, it'll be another day.
I'm already making this a 2-day lesson. I was never planning to make it a
So
1-day.
that Gabe,
You just didn't inform us of her plans.
Huh? Yes. We will stop after the half angles. 2. Which would leave you plenty of homework time tomorrow and time to ask questions over the summer. So the first half angle identity is sine, because we always start with sine. What I mean when I say half angle identity, that means I took some angle and multiplied it by 1/2. You would believe how often somebody doesn't know what I mean when I say half angle identity. So that can be looking like, oh my gosh, that can look like either of these. I prefer this one because it's a little more obvious, but it could also be written as u/2 or theta over 2 or x over 2, whatever our angle is. Our half angle identity for sine is equal to positive and negative square root of 1 minus cosine of angle u divided by 2. Yeah, that's a u. We also have a cosine half angle identity.
Is that multiple?
No, it only has one.
Sorry.
It is also equal to positive negative square root of 1 plus cosine of u over 2. And then we have a tangent half angle identity as well. And that is equal to the positive and negative square root of 1 minus cosine of u over 1 plus cosine of u.
so is the square root part like the formula part?
Yeah, so this whole thing is the formula part. I call it an identity because that's actually technically what they're called, but
I just didn't know if it was
Formula's the
another
same.
way to use it.
no. And then we're going to do some examples. As I said, there are 2 examples for this set of identities.
Why is cosine like an attention box?
It just is. I don't know.
Oh, in cosine.
It's kind of funny how it breaks down that way. Okay, are we ready for an example or are we still writing? Okay. And then after the set of notes, I believe there's one more set of special angle identities that we're going to write, and then that will be it. And then we'll do more stuff.
I thought you were gonna say quiz or something.
Well, tomorrow we're going to finish these notes, and then there's one more set of identities for the next set of notes. No. We're writing the rest of these notes tomorrow after these 2 examples.
You said the special angles. How are we writing those?
That we have been writing them. These are what they are. These are special angle formulas and identities. Okay. First example. Sorry, honey, I didn't mean to confuse you.
Well, I'm still.
She said it's a no way for that.
Broke my legs, that's fixed here, so.
I do too. I feel like it's an underrated color.
Magenta.
Okay, well, you just run it back.
Is that a 22.5?
Yes, that is 22.5. So we are clearly going to be using our half angle identities on these, since that's what we just wrote. So the directions here are to find the exact value for sine of 22.5 degrees. In order to use our half angle identity, I acknowledge that 22.5 is equal to 1/2 of 45. So our U angle that we're actually going to be computing with is 45 degrees. So I took the 22.5 that I was given. I found out what it was 1/2 of, and then that angle is the angle I'm going to use in my identity. Because I wouldn't want to take half of 22.5, that would just be ugly. Whenever we change any of these, we always try to change them into an angle that exists on the unit circle, since exact value means that we're pulling from the unit circle. So when in doubt, it should always come back to one that's on that circle that you have. So the first thing I recognize after identifying my U angle is the trig function I'm using. Here that is sine. So my sine half angle identity says that this is equal to the positive and negative square root of 1 minus cosine of my U angle, which is 45 degrees, over 2. And then I will simplify this using values from my unit circle. So the only value I have to replace is cosine of 45 degrees, and what is that equal to? Square root of 2 over 2. So then this is equivalent to the positive and negative square root of 1 minus the square root of 2 over 2, all over 2. Of course, I don't want to leave it like that because that's really ugly. So I will try to simplify this. We don't like a fraction on top of a fraction as our final answer. So whenever I'm dividing by 2, that is the same as what? Multiplying by 1/2. So then this can be written as the positive negative square root of 1/2 times 1 minus the square root of 2 over 2. I can go ahead and multiply that 1/2 in. When I do, I get 1/2 minus the square root of 2 over 4. I'm going to go ahead and simplify this farther by turning 1/2 into a denominator of 4. So 1/2 is equivalent to 2 over 4. Which allows me to write it as 1 fraction. So it becomes this positive and negative square root of 2 minus the square root of 2 all over 4. My last step then is to simplify this by seeing if I can take a perfect square out of this. Yes or no? I'm hearing yeses and nos. The 4. My denominators are perfect square. So then this is equivalent to the positive and negative square root of 2 minus the square root of 2 all over 2, where 2 is not under the square root anymore. Because I was able to take the square root of 4 and it was 2. No, because I can't take the square root of 2. And it wasn't being multiplied in, so I can't do that. If there was a 2 in front of the square root, I could do that. So then this is the final part. I currently have 2 answers given to me. I need to decide which one I'm going to use. And that is strictly based off the placement of the angle that I have been given. So I was given U equal to 45 degrees. What quadrant is a 45-degree angle in? Quadrant 1. Is cosine in quadrant, no, not cosine, sorry. Is sine in quadrant 1 positive or negative? Positive, which means I'm using the positive answer from this. Since sine was positive in quadrant 1.
That's right one.
No, but I'm telling you in case you go back and look and you're confused. So we identify where the angle exists and we find the positivity of our specific trig function for that quadrant. Questions, concerns, or issues with that one? Okay, we'll do one more and then we will give this one a break until tomorrow. So we're doing the same thing, except this time, I would like to use a half angle identity to find the value of cosine of 112.5 degrees. Huh? Yeah, hold on. Yes. So Ismail already did it. When I'm given something like this, I need to find the angle on the unit circle that is twice whatever this angle is. So I just take it and I multiply it by 2. And when I do, I get that this is equal to 1/2 of 225 degrees. So the angle I'm using is 225 for my identity. So we multiplied it by 2, and then that's the angle I'm actually using. I want to use this one because it exists on my unit circle. Yes, ma'am. Oh, yes.
They give us the,
Mhm.
like an angle like that, do we always expect that it's probably half of a bigger angle?
If it's a decimal like that, or if they say to use the half angle identity, then yes. Yes. Are we good? Okay, so now let's go ahead and do my identity. So obviously I recognize that it's a cosine and it's a half angle, so I go to my cosine half angle identity. And I recognize that that is equal to the positive and negative square root of 1 plus cosine of 225 degrees over 2, and then just like on the previous problem, I just have to simplify this. So what exact value am I pulling from my unit circle? Negative square root of 2 over 2, because that's what cosine of 225 degrees is equal to. So then this becomes the positive and negative square root of 1 minus the square root of 2 over 2 over 2, and it's going to simplify just like the previous problem. Ismail's not allowed to answer anymore, for the record. So somebody tell me what we're going to do to start simplifying this. And by take the 2 out or get rid of the 2, we mean that we are going to multiply the numerator by 1/2. Good. So then this becomes positive and negative square root of 1/2 times 1 minus the square root of 2 over 2. I simplify that by multiplying the 1/2 in. And I get 1/2 minus square root of 2 over 4. What next? Create a common denominator so I can put the 2 fractions together. Here that means turning the 1/2 into something over 4. So I multiply the top and bottom by 2, and that gives me 2 over 4, which I can then write as 1 fraction, which becomes 2 minus the square root of 2 over 4. I can reduce it by taking the square root of 4 because I know that that's a perfect square. And this becomes positive and negative square root of 2 minus the square root of 2 all over 2. And then I'm finished, right? No, what do I have to do? Decide the positivity of my answer. So what quadrant does the angle 225 degrees lie in? I sensed some unsurety. What quadrant does 225 degrees lie in? 3. Good. So is cosine positive or negative in quadrant 3? Negative, which means I need the negative answer.
I like that we don't really have to use like a calculator.
I like it too.
It was so weird doing the homework and not using a calculator. I was like, what?
And you will need to be confident and able to do this without a calculator because you will have a no calculator portion to your next quiz and test. And you will have these types of questions on it.
I don't know how you could use a calculator.
You could really just use it to check it, but that's it. Okay, questions, concerns, or issues? Okay, so homework is on Canvas. You can definitely do some of it. We have one more set of identities to go for this lesson, and it is these squared angle identities. So any questions that have that, you can just kind of ignore them.